Hello, thanks for clicking the link or scanning the QR code. Thanks for joining me anyway, how you found this video. Why u-subs for integrating functions of a type, some constant multiplied by a function to a power n, and then also where the derivative of that said function is also in the product of the expression to be integrated. This here is the same idea, but by putting f of x to power n on the denominator. It's basically this here if n were a negative value. So n or n there, because n is allowed to be an integer, this is the same as that, it's just a different way of how it can look. Because I could rewrite this if I wanted as k f dashed x, f of x to the minus n. But if n is an integer and can be negative, it makes no odds. So the key thing is, why do it? So why do I teach this method, which I'm going to come on to in a moment. First of all, I'm going to explain why this works. It's essentially an application of the chain rule in reverse. So first of all, let's just consider differentiating a function y if y were some constant a multiplied by a function of x, and all that being to a power of n plus 1. So let's imagine if we were to try and differentiate that. How would we do it? Well, because we've got a function here to a power, and if f of x is itself as a function, then we need to use a chain rule. So let's set u as f of x and apply the chain rule. Remembering what the chain rule is, it's dy by dx equals dy by du multiplied by du by dx. So here, if y is a f to the x all to the power of n plus 1, if I differentiate y with respect to u, the power will come to the front. So we're going to have n plus 1 multiplied by a f of x, then we're going to drop this power by 1, so this will just become to the power n. So dy by du is this, and then du by dx. Well, if u is f of x, if I differentiate this with respect to x, I can just term that f prime x, or as I say, f dashed x. So this is what we get. So I can neaten this up and put the f dashed x near the front and write it in this form, just a simple simplification. So because a was just a constant and n was a power, which is also just a constant number, n plus 1 is just a constant, a is a constant, and so a multiplied by n plus 1 is itself just going to be a new constant. So let's call this constant a multiplied by n plus 1, whatever this is, let's call that k. And so we can see here, just simplifying and introducing this as k, just for simplicity, it's one and the same as k multiplied by the derivative of f of x multiplied by f of x all to the power n. So what does this show? What does this actually mean? Well, that means that if we remember that integration is the reverse of differentiation, if we were to integrate a function like this, where we've got some constant multiplied by the derivative of a function multiplied by the function itself to the power n, it will always differentiate to something like, so I mean to say it will always integrate, rather I mean to say, to something like a f of x to the power n plus 1. So it all goes in terms of just the f of x. So essentially what I'm saying here, the conclusion to make is, if we have to integrate a function of this form here, it will integrate back into something like this. It'll be some multiple of fx to the n plus 1, and I've called the multiple here a. Okay, so let's think about this slightly deeper. What this means is, with enough practice, you might be able to actually integrate things like this by inspection without using a u-substitution. That might get you thinking, well, why has he put a title u-sub here? And we're going to come on to why I use the u-sub and not this method. But just introducing this method which Edexcel use, and I'm not knocking this method or saying it's not a good method, it is, but I think it comes with practice. Let's just imagine integrating 5 cosine x and sine x to the 4. So just spotting by inspection, sine x would differentiate to cosine x. So we could think about what would, just in thought bubble here, what would sine x to the power 5 differentiate to? So if I call this give myself a bit more space actually. If I just were to call this differentiating u to the 5, where u is sine x, and use a chain rule, you should hopefully see that dy by dx, differentiating sine x, to the power 5, I can write it like this, or I can put sine 5x, is going to be differentiating it with respect to u, so I'd have 5 coming to the front, and then u to the power 4, then differentiate u with respect to x, which is cos x, which of course is 5 times cos x, and then u was sine, wasn't it? So that goes to sine x to the power 4. So if I differentiate sine to the 5x, I get that. So therefore, if I'm integrating this very same thing, that will become sine to the 5x. If you can do that and spot how to do that, that's when you know you're rocking and rolling. That is when you've really got this mastered. Always do plus C if we're integrating, of course. I think that is not immediately obvious to see. And it's much less obvious when you have a harder integral that is a bit more disguised than this one. For example, if you've got a fraction or like a negative power, it's quite hard to spot to do that. But with practice, as I say, it can be done where you can do it by inspection. So that's quite quick with practice. So why am I mentioning u-subs? Well, I'll show you how to do it using a u-substitution. So if I just clear out some space here and just scroll down slightly, what we could do is think about why u-substitutions work instead. So, to give you the idea of how they work, I'm going to actually show you algebraically. So let's imagine we're wanting to integrate k f dashed x, f to the x to the power n. So using u-subs, how would you do that? So k f dashed of x, fx to the n. This is the general idea of why the u-sub works. So in general, this is the general case. If you're integrating something where it's a constant multiplied by the derivative of what's here, maybe to some power, maybe not, we can set u to be f of x. Just as above, we set u to be f of x here. But now we're doing the same, but in reverse. So if we do that, set u to be f of x, then of course we can differentiate that with respect to x. So du by dx, generally speaking, is of course f dashed of x. So times by dx, divide by f dashed. So we can say that dx is the same as du divided by f dashed x. So this transforms in terms of u to k f dashed of x. F of x we can now just say as u to the power n, and then dx is one and the same thing as du over f dashed of x. So doing it this way instead of by inspection, we can see here you'll always get this cancellation. F dashed will cancel with f dashed on the denominator. K, of course, is just a constant, so we can take the k to the outside of the integral and just integrate u to the n with respect to du. So we're going to add 1 to the power and divide by the new power, then plus, of course, the constant of integration. So that's going to give us k u to the power n plus 1, all divided by n plus 1. You can put the n plus 1 there, plus c. And k over n plus 1, again, is just some constant. So I'll just call that capital K, or weird fantasy K, some constant u to the n plus 1 plus c, which is essentially, if you look here, what we said it would be. Some constant multiplied by f of x to the power n plus 1. So why do I do it that way rather than just by inspection? I'm going to try and explain why I use this u-sub method next. So, why don't I just teach the reverse chain rule, essentially, then just adjust the constant instead of introducing yet more substitutions? So we've done some substitutions already, so why am I suggesting you do more of them? Well, just to explain, a few reasons, in my opinion. Essentially, I don't think it's always obvious to spot and adjust the constant like using the reverse chain rule asks you and requires you to do. Okay, with practice it becomes easier, but if you've got some really awkward trig functions or some negative powers, it's quite hard to spot, and I think it's much easier to spot if you've got a function and you can just see somewhere within the integral the derivative of it. If you can spot the function and the derivative itself living within the same function, that's an easier clue to spot to do a u-substitution. So initially, the book method I don't think is that obvious. If you disagree with me, that's great in a way. You can do these quicker. Second reason, u-substitutions are just a massive part of calculus. So the more practice application you get with them, the better. So my feeling is by doing more u-substitutions, it's just going to get you better at doing them. And because they're going to be on your exam almost guaranteed, it can't hurt to have a bit more exposure and practice with them. The third one I wrote down, if I teach you this u-sub method, it doesn't necessarily force you to use it. You can still use the adjusting the constant method. By all means, do that when you feel ready. But I do think the u-substitution method is a fairly nice introduction to it and will allow you to see the patterns in your own way when you're ready to. A couple of unofficial bullet points I want to add here, which I didn't really want to put in the recording, but just me being me. Another thing I'd say is, there's something inherently satisfying, I think, about cancelling things. So it's inherently satisfying to cancel. And as well, Symbolab. If you've not heard of Symbolab, if I've not mentioned it, check it out. I'm not getting sponsored for saying. I'm pretty sure Symbolab had a bigger fish to fry than my little channel. But Symbolab also use u-subs when they use their algorithm or whatever software to actually work out derivatives. Symbolab, if you type in on Google Symbolab followed by what you want to do, for example, you could Google Symbolab differentiate or Symbolab integrate. It's a brilliant website. It shows you step by step how to integrate things, and it's a good check for your homework. I'm not saying to cheat, because obviously if you've used it, but Symbolab I think is really useful. So just another reason why this video might be useful. Check out Symbolab, even if you think these explanations are pants. Symbolab is really good. Anyway, let's crack on and let's do some worked examples. So how does this u-sub work in practice? Well, here's some examples. So what we do here, we're just going to term u, the function which is to be differentiated or appears to be differentiated with the integral. So have a look here. We've got x cubed minus 7 and 3x squared. So if you spot, if I were to differentiate x cubed minus 7, I'd get 3x squared. And so because I can see the derivative within the same integral, I'm thinking that's a u-substitution. And you term u to be the thing which then differentiates to this. So u I'm going to pick as x cubed minus 7. So let's do that. So this is going to become, in a moment, something different which will cancel and work much nicer. So first of all, we need to work out du by dx. So differentiate u with respect to x gives 3x squared. So therefore, rearranging in terms of dx, dx will just be du divided by 3x squared. So we're ready to transform. So dx becomes this, and the integral transforms. We'll leave 3x squared as it is. X cubed minus 7 we said was u, and dx is now going to become du over 3x squared. So this here, du over 3x squared, and x cubed minus 7 becomes this. Hopefully you can see that the 3x squared will cancel nicely with that 3x squared, and so it just becomes much easier. I'm now just simply integrating 1 over u with respect to u. That's a standard result which we need to know. If you're integrating 1 over u with respect to itself, that's going to give us ln of u. So we get ln mod of u plus, of course, c. Fill in what u was, revert back to the original variable. So ln of u, which is x cubed minus 7 plus c. This one. So sine to the 5x, what would that differentiate to? Well, the spot here is that sine differentiates to cos. Therefore, we can set our u to be sine x. So this one, we're going to go for u is sine x. So we need to take du by dx. So differentiate sine x, differentiate u with respect to x, sine differentiates to cosine. Rearrange to get it in terms of dx. Dx, therefore, will be du all over cos x. So that's going to become, instead of dx, I can term it like this. Transform the integral now. That 10 I can put to the outside if I want to, or leave it there. I tend to take the constants to the outside. So I've got 10 on the outside. Cosine x, sine to the 5, because u is sine x, sine to the power 5 is u to the power 5 in terms of u. And then dx, we said, is the same as du all over cosine x. So again, nice cancellations. So we're going to have 10 integral of 1 over u to the 5. In fact, I'll call this u to the minus 5 because in index form, I believe it to be easier. Du. So we're going to have 10. We're going to increase the power by 1. So we're going to have u to the minus 4 and divide by the new power. So divide by minus 4 is the same as multiplying by minus 1/4. Plus, of course, c. Simplify and revert back to the original variable. So minus 10 over 4 is the same as minus 5 over 4. So it's the same as minus 5 over 2. What am I thinking? Minus 5 over 2. U to the minus 4 is 1 over sine to the power 4. But 1 over sine is cosec. So 1 over sine to the power 4 is the same as cosec to the power 4. Plus, of course, the constant of integration, c. So again, that transformed quite nicely, I believe. You'll agree with me? I hope you do. The next one. So I'm hoping you can sort of see and believe me when I say I don't think it's that obvious to just do the reverse chain rule. When you can, you know you're getting really good. Here, what I'm going to do, I spot that if I were to have a look at ex plus 1, if I differentiate ex plus 1, I'd get just e to the x, which is what the top is, multiplied by some multiple. So again, that's my clue, a u sub will work. Therefore, I'm going to put my u as e to the x plus 1. So let u equal e to the x plus 1. Therefore, differentiate u with respect to x. 1 disappears, e to the x just differentiates to itself. So therefore, in terms of dx, I can say that dx is going to be du all over e to the x. So dx here is the same thing as du over e to the x. Now we're ready to transform this integral. 3 to the x, leave as is. This is u squared, so that becomes u squared like so. And then dx is now replaceable by du over e to the x. Again, you'll see some lovely, satisfying cancellations, or maybe just me being weird. E to the x there cancels with e to the x there. I can now take the 3 to the outside or leave it in, your choice entirely. I'm going to take it to the outside, so it's going to be 3. And then I'm going to have, after cancellations, just 1 over u squared du. 1 over u squared I can write as u to the minus 2 du. Integrate, so increase the power by 1, add 1 to minus 2, we get u to the minus 1, divide by the new power. Dividing by minus 1 is the same as multiplying by minus 1, so just stick a minus in front there. And of course plus c. Final step, replace what the original variable was. We were talking in terms of x, and it's to the minus 1, so I've got minus 3. Because it's to the minus 1, I can put it over what u was. U was e to the x plus 1, like so, then plus c. These bottom ones are actually slightly simpler, and in fact a is very similar to the example I showed you where you can use just the reverse chain rule. But in this particular case, using u-substitutions, I think it's a bit easier on the brain. So sine differentiates to cos, therefore let's put our u as sine x. So if u is sine x, I can differentiate u with respect to x. Sine differentiates to cos, so therefore dx, I can rearrange and get it's the same as du all over cosine x. So we can transform the integral now. So cos x, leave as cos x. Sine cubed, I can now say it's the same as u cubed, because u is sine x. And of course dx, we said, is the same as du over cosine x. Hopefully you see here, we get the cancellations. So cosine x, u cubed du is what we're integrating therefore. Easy. Year 12 stuff this. So add 1 to the power, divide by the new power. U to the 4 divided by 4 gives us a quarter u to the 4 plus c. But of course u, remember what u actually was, we said u was sine x. So we're going to have a quarter sine x to the power 4, which we can say is sine 4x plus c like this. B, again, just check this inner function to the power 6. X squared plus 5. What would that differentiate to? Well, x squared would go to 2x, lucky here, big clue, and 5 disappears. So because this function here differentiates to this bit, again, massive clue, u sub will answer our prayers. So this time again, we're going to put u as x squared plus 5. du by dx is 2x, so therefore dx is du all over 2x. So I can switch dx in terms of du. Now I can transform the integral. I don't think it's technically called transforming it, but I think it's like a transformation because it looks much different. So we get 2x. This bit here is just u to the 6. And dx, of course, is du over 2x. So 2x here cancels with that 2x, and therefore you can see it becomes, with that cancellation, I just think it's satisfying because it just looks so easy now. I'm just integrating u to the 6 du. Takes me back to year 7. So add 1 to the power, divide by the new power. Can get 1 over 7 u to the 7. Plus c, of course. Final step, you can guess what I'm going to say, hopefully. Return to the original variable. We're actually talking about x squared plus 5 as u. So then we just say 1/7 x squared plus 5 all to the power 7 plus c. The next one I've made deliberately as a challenge for you. So what I can suggest we do here, it already looks evil enough. Let's take that 8 to the outside of the integral. Let's say it's the same as 1/8. Now let's partition this into something a bit easier. So I've got cos cubed over sine to the 5. Let's call that cos cubed x over sine cubed x. Match the powers up. And then I'm still going to have another 1 over sine squared. All with respect to x, of course. So let's think about what cos over sine is. Well, cos over sine is the reciprocal of sine over cos, which is tan. Reciprocal of tan is cot. Because it's cubed, this thing here is going to be cot cubed. And this one here, 1 over sine squared, 1 over sine is cosec. So 1 over sine squared is the same as cosec squared. Just so it looks more familiar, I'm going to put cosec squared first. So it's got cosec squared x here. And then that's going to become cot cubed. Like so. You might be thinking, well, it still looks absolutely awful, this. If you do have an integral, especially if it's a trig integral, and it just looks heinous, and you've tried, and you've tried, and you've maybe cried, just be thinking, could I check the formula book? Is it maybe a standard result job? And this one actually is, although it's not particularly obvious. We need to think formula book and then check what cot differentiates to. And you should find that cot differentiates to negative cosec squared. In other words, because cot differentiates to some multiple of cosec squared, we're good. That's therefore the clue to tell us what to set u as. We're going to set u as cot x. So that's what we're going to do now. So, setting u as cot x, we can work out du by dx. So differentiate cot x with respect to x. This is a standard result. You could, if you wanted to, if you're really not sure and want to convince yourself just for practice, nothing else, set cot as cos x over sin x and use a quotient rule to convince yourself. Using that way to convince yourself or the formula book, you should find that du by dx is negative cosec squared x. So rearranging in terms of dx, dx is going to be du over minus cosec squared x. So we're about ready to go now after a bit more legwork. I'll put this in as like one which looks harder, just show that you can do hard ones still using u-subs. So transform the integral. 1/8 will stay put. Then we get cosec squared x. We said u was cot x. This is going to be u cubed. And dx is the same as du all over minus cosec squared x. So that cosec squared cancels with that cosec squared, but just be careful of this minus. Because you've got the minus, I'm going to take the minus to the outside. So what we're going to have there, I can say that 1/8 is now minus 1/8. Then just got the integral on the inside, u cubed with respect to u. So I'm going to get minus 1/8. Add 1 to the power, becomes u to the 4. Divide by 4, 1/4 u to the 4. Remember the concept of integration, plus c. Simplify now and return to the original variable. 1/8 of a quarter is a 32nd. For minus, of course, so we've got minus 1 over 32. U, which is cot x, so we're going to have cot to the power 4x plus c. So that's one form which works. So I hope you found that to some extent useful. And hopefully nothing else. Now I've convinced you, almost feels like an apologist's video explaining why I'm doing something, but here you go. That's why I use u-sub, that's its power. Thank you for listening, and again, if you do want to just do these by inspection, if you're confident that you can convince me that you're good enough, by all means do, but I do think there's a lot of merit in just using the u-substitutions. Thanks for watching, I'll see you soon, take care.